another day. I call and never speak, and you would say that nothing's changed at all. And again, it seems we meet in the spaces in between. We always say that it won't be long. Oh, but something's always wrong. Something's always wrong. Something's always wrong. Hello everybody, welcome to this week's edition of Video Notes for AP Chemistry. That's right folks, this is for AP Chem. So if you're looking for the Chem notes, find a different video. Alright, let's go ahead and get started. We're going to be talking about ions and ionic bonds. So basically here's the rule, right? The rule of octet. Very important rule. It's generally just a rule of thumb though. It's not a hard and fast rule. But it says this, right? Elements or atoms tend to gain, lose, or share electrons to acquire a full octet in their valence level, right? So generally that's eight electrons, right? So if you've got any levels from 2 up to 7, right? A full p and s orbital contains 8 electrons. However, if it's just a first level, for example, hydrogen or helium, they are only going to have 2 electrons in that valence level, and the rule of octet changes a little bit. Now this can also be flexible for larger atoms, especially things like xenon, which will tend to form compounds and have more than a full octet in it, as well as other atoms that are over on the nonmetals side of things. Well, let's move on here and talk about ions and ionic bonds. So when an ionic bond forms, it forms between two different kinds of elements, right? Metals, which we find over here on the left side of the periodic table, and nonmetals, which we find over on the right side. And what makes these two elements stick together is the fact that they are opposite charges. Okay, and what happens is what forms is called an electrostatic bond. Okay, because they're opposite charges, they are attracted to each other, and that forms the compound. So how do these ions form? Okay, here are some general charges for things. Okay, group 1A, right? That is the alkali metals. Okay, group 2A, that's your alkali earth metals, right? And be +2. Now the D block tends to be hard to predict, okay, and they can vary anywhere from a +1 to a +4 depending on the element and the energy involved in the reaction, okay. And you keep moving across, they get much more predictable. Group 3 is +3, okay. Group 4 is +4, all right, although tin and lead can sometimes be +2, and so on. Then we get to the nonmetals, okay, which generally form anions or negative charges because they take electrons. All right. However, as you get towards the bottom of the anions of this group 5A, which includes nitrogen and phosphorus, you find that the metals down there tend to be positive because metals tend to have a low electronegativity and want to give away electrons, right? Then here we have the -2, which is the oxygen group, and -1, which is your halogens. You can go ahead and write that on your periodic table for reference if you can't remember it, but we've memorized a lot of these charges, right folks? So let's talk real quickly about D block cations. These are those unpredictable transition metals, the ones that you really have to kind of memorize because there's no prediction to them. And that's kind of because of this, right? These atoms will almost always lose their S level electrons, which tends to be 2 of them, right? But then they'll also tend to lose some of their D block electrons, and it's hard to say how many they will lose or not. So, for example, iron here, right, will either form a 2+ by losing its 4 S electrons, or it'll form a 3+ by losing the S electrons as well as one of its D electrons. So it's hard to predict when that will happen, okay, and what ions will form. But that's why we had to kind of memorize a lot of those. All right, so to define ionic bonds, right, this happens when there's a transfer of electrons, right, where electrons move actually from the metals to the nonmetals, and the bond forms due to electrostatic attraction, right? This has a lot to do with electronegativity and the electron structure of these elements, right? So it could also be defined a slightly different way, right? Cations, right, form electrostatic bonds with anions based on opposite charges. And you could also have in here something called a polyatomic ion, right? Something like carbonate, okay? That is an ion, but also has some different kinds of bonds holding it together on its own. And that's okay. We will talk more about these polyatomic ions in class. All right, just to give you a little bit more of a visual representation of an ionic bond forming, here we have sodium actually giving its electron to chlorine, okay, making sodium a positive charge, right, and chlorine a negative charge. Okay, therefore they both achieve stability by gaining full outer levels of electrons. Now, when we talk about ionic bonds, we are talking about bonds that are very, very strong. Okay, so that means it requires a lot of energy in order to melt or boil these solids, right? So think of salt, okay? You're not going to melt salt at your house. It's a very endothermic reaction in order to melt that, which means it requires a lot of energy to put into that reaction in order for it to happen. So here we see, right, a value for that, right, the delta H, which is the change in heat in order to break those bonds and break down the lattice or the crystal structure of salt. Okay, that's a lot of energy, folks, 788 kilojoules to put into it in order for that to happen. So what affects the melting points of these ionic compounds? Well, we're back to this, Coulomb's law, right? Our fave, isn't it? Okay, so here's the equation for it, all right, and K's got this constant. That doesn't, that's not a big deal. You're not going to have to use that or anything like that, okay? But remember this, right? This D here is the distance, okay, from between ionic centers. Remember, most of the positive charge in a atom is concentrated in a very small spot in the middle. You also have this too, right? The Q, which is the charge of a single ion. So the difference between a -1 ion and a -2 ion is going to make a big difference, right? That almost doubles the attraction or the force of attraction between atoms. So think about this with me real quick, okay? What affects the melting point of solids? Well, remember a couple of things, right? First thing is this. First thing is distance. How far are the centers of those ions apart? And the second thing is going to be this, the charge. Do you have an atom that has a double charge, like a double negative, for example, oxygen? Or do you have something that just has a single negative, like chlorine? That's going to make a difference in the attraction between the ions. So, which compound from each set has the greatest melting point and why? Well, we'll talk about that in class, but I want you to take a quick guess here. Right? Is it lithium fluoride or lithium iodide? Magnesium chloride or magnesium oxide? Is it sodium fluoride or magnesium iodide? We'll talk in class, folks. Here's another problem just like the ones before, right? Which of the following would have the highest melting point? Just so you know, those little red ones there, those are fluorides. Okay, so that's fluorine. You can see that's consistent in each one, but the positively charged metal is different in each one. So which one is going to have the higher melting point? Again, you take a guess now, and we'll decide in class. All right, some properties of ionic solids. They are very strong bonds, right? Very strong charge forces that attract them together. That's what this means, the Coulombic forces. That's due to charge, right? So they have very high melting points. They're very hard, and they are not very volatile. In other words, they're very stable compounds because of these very strong bonds between the atoms. Another property of these ionic solids is their rigidity, right? They are not malleable or ductile, so they can't be formed or shaped into anything. If we do form or shape them, they will cleave along planes, and that's because the atoms are arranged in a repeating pattern, as it says up there, to maximize attraction and minimize repulsion, right? So if we do apply force, the atoms don't move, they just slide along planes where the atoms can break off from one another. Maybe it's a weak point, maybe there's some impurities in the crystal or something like that, but that's how we can shape them. We can't mold them, we can only break them along certain planes. Okay, last thing is this. These compounds tend to be soluble in polar solvents, and if you're like, what's a polar solvent? Well, a polar solvent is this, water, right? Water is a polar molecule, okay? And once they are put in solution, they can become conductive. So the only time that a ionic compound is conductive is when it is in a solution. When it's in a solution, the charges are separate from each other and free to move. However, if they're in a solid, those charges are stuck in place, right? Like we saw on the last slide, causing them not to be conductive of electricity. Okay. Well, thanks for tuning in, folks. Appreciate you doing this for me, and it helps us move along faster in class. So we'll talk about this on Wednesday in class, and kind of debrief what was in these video notes. So thanks for tuning in, and have a great day. Bye-bye.